Hey everyone. In this video we're just going to go over a few more examples of how to find molecular shapes using our approach of drawing Lewis structures and then making a determination based on what we end up with on various central atoms in our compounds. So I'm going to do a bunch of quick little examples that just have a single central atom, and then I'm going to go and do one that has multiple ones so that we can kind of get a handle on when you decide what things are going to count as central atoms in your compound. So I'm going to go ahead and just flip over to my first set of examples here, and I'm going to try to do some weird ones here today because there are a number of molecular geometries that don't really happen very often, and especially are pretty much only allowed when you have atoms in the middle of your compound that can do expanded octets. So that is something that we're going to look at specifically here today. And I'm just going to go through each of these in turn. I'm not going to spend a whole lot of time on the process for drawing the Lewis structure for all of these, but I'll try to do each of these in turn, and by the end we'll have some good examples to work with. So for starters, starting with this sort of odd-looking compound that we have in the upper left-hand corner of the page, we're going to start just by identifying the least electronegative atom, because that's going to be the center of our compound. And if you looked at the periodic table and tried to figure that out, we know that fluorine is super electronegative, and oxygen is pretty much runner-up to that, because it's right next to fluorine on the table. So iodine is going to be our atom of choice to be the center of this molecule. So I'm going to put iodine in the middle, and then just to try to keep everything fairly as simple as possible, I am going to go ahead and array the oxygens and the fluorines around this. And then the next step is to fill in the Lewis structure. And the first thing we're going to have to do is count up the total number of valence electrons. So we'll get some practice with that just to start with. We should have 7 from our iodine, but then we also have another 7 from the 2 fluorines, because they're all halogens there. And then finally we have 2 oxygens, and each of those is going to be worth 6 in our total here. And then finally, it's always really hard not to forget about this, but we have an extra electron that comes from the charge that we have on this. So we should end up with a total that looks like this, and our total here should be 34 if we add that up. So next, we need to start building our Lewis structure, and I'm going to go ahead and connect all of these atoms together. That gives us a total of 8 electrons that we're taking off of our total. So we should end up with 26 left over. And then we need to start distributing lone pairs around this structure and try to use up as many electrons as we can here. So I'm going to go around and distribute pairs in turn to try to get everything evenly distributed as much as possible. I'll go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and now we have all of our outer atoms satisfied, which leaves 2 electrons left over. And in this case, we don't have any other option but to put those on the iodine. Hopefully we can understand why that is, because in this case, iodine is the only atom in this compound that can do expanded octets, and so those extra electrons have to end up there. If I was being really complete about my Lewis structure, then I would bracket it and put a charge on the outside, so I'll get rid of my math here so we can do that. And we should end up with a structure that looks like this. So then the question is, what is the electronic geometry and the molecular shape that we're working with here? So that would be the second part of this. Hopefully what we can see is that we have 5 charge clouds around this. There are 4 bonded groups and 1 lone pair. So the geometry is going to be trigonal bipyramidal. And because there's 1 lone pair, we have to think about how that's going to affect the shape. Now, it's worth remembering that trigonal bipyramidal geometry has a couple of different places where substitutions can be made in it. If we have a central atom that has this bond arrangement, we know that there are non-equivalent positions around the center here, because there's no way to arrange 5 things and have them all exactly as far away from each other as possible. So we've got these axial groups that are on the top and the bottom of my diagram here, and then we've got the equatorial groups that go around in the center, right? When we substitute in lone pairs in a geometry like this, we're going to actually take away from the equatorial positions first, because those are the ones that have the most room and are furthest away from the other atoms, relatively speaking. And what we know about lone pairs is that they like to take up as much space as possible. So if I'm going to add a lone pair to the structure, and I'm just doing this as an example, I would probably pick one of those equatorial positions to include that lone pair, right? So what we're left with is something that is commonly referred to as a seesaw shape, because we have sort of a bar that is made from 3 atoms all going in a line, and then we've got 2 angled pieces that are coming off of the side there. So our shape for this one is going to be seesaw as our final answer. The last thing that I want to point out for this is whether or not we have a polar or a nonpolar molecule, and this should be pretty much a no-brainer for us, because since the molecular shape is not symmetrical, we are going to end up with a polar molecule regardless of how these atoms actually end up arraying themselves around the central atom. So we would say this one is also polar because we have a structure that's asymmetrical. And we can make that call just based on the symmetry of the molecule without having to worry about actually drawing vectors of the bond dipoles or anything. Next up, we have ClF₃, and this one is a bunch of halogens stuck together, so we know we're going to have a total of 28 electrons to work with, because it doesn't look like there's a charge, and it looks like we have 4 atoms that should have 7 valence electrons each. I'm going to put the least electronegative atom in the middle of my structure again, which is going to be chlorine here. And then we have the fluorines around it. And we'll take 6 off of our total for drawing single bonds to start with. So we're left with 22 here. And then we have to start arraying our lone pairs around, so I'm going to do that real quickly. And at this point, we should have a total of 18 electrons accounted for. So I'm going to take that away from 22, and we should end up with 4 electrons left over in that calculation, which means that we have to put 2 lone pairs on the chlorine. Again, we don't have a choice of where to put those because chlorine is the only atom in this structure that can take an expanded octet. Now hopefully what we can see is that we have a trigonal bipyramidal electronic geometry because we have 5 different charge clouds, 2 of which are lone pairs here. And just like before, we're going to put those lone pairs in the equatorial positions around this geometry as long as we have those available. So we're going to end up getting rid of 2 of the equatorial positions. For clarity in the model, I'm just going to take the ones on the right this time, and we should end up with a structure that has those then missing when we are trying to understand the molecular shape. Hopefully what we can see here is that we have roughly 90 degrees here for the angles that we're going to have in our structure, and that's why we call this one T-shaped. So to finish up this structure, I'm just going to include those in our list here. We have an electronic geometry that is trigonal bipyramidal, just like before, but because we have 2 lone pairs on the central atom, we're going to end up with a T-shaped molecular shape. And because that shape is asymmetrical, once again, we have a polar molecule here. It's just as simple as that. Last example in the first row here includes a xenon and then an oxygen and 4 fluorines in this sort of odd-looking formula for a compound. Once again, we're going to take the least electronegative atom and put it in the middle. This time we're definitely going to pick xenon because xenon does have an electronegativity value, but it is going to be a lot lower than oxygen and fluorine. So we'll put xenon in the middle, and then we'll array the rest of the atoms around it, and I'm just going to draw this in a 2-dimensional way for starters. Then we have to add up the valence electrons so that we can start building the structure, and if you do the math here, you should end up with 42 as the total. So I'm going to take away 10 electrons right away, drawing single bonds to my central atom. And that leaves us with 32 to distribute around the rest. Now some folks might see what's already going to happen here. If I do continue to array lone pairs around this structure, I will end up with a situation where we have 2 electrons left over because we have a total of 30 that we've just distributed around the model. And that leaves us with 2, which means those are going to have to go on our xenon in the center. Xenon, again, in this molecule is the only atom that can form expanded octets here. So now we have to assess what the shape and the molecular geometry is. We'll start with the molecular geometry. And hopefully what we can see here is that there are 6 charge clouds around xenon. One of them is a lone pair, so its electronic geometry is going to be octahedral. And then we have one lone pair. And it doesn't really matter where we take from this three-dimensional model of electronic geometries, because no matter where you look on here, we have equivalent positions. So if we just substitute one of those, we're going to end up with something that looks like a pyramid with a square base. And I'll just take from the bottom here to illustrate that kind of in the most conventional way possible. And if we put a lone pair on the bottom here, hopefully we can see that we're going to end up with a square pyramidal geometry here. Just like all the other examples so far here, this is an example of an asymmetrical structure, so we're going to know right away that this is a polar molecule because of that. Next up, we have some compounds on the bottom here, some of which we probably have worked with a little bit in class, and they look a little bit more familiar. So once again, with phosphorus pentafluoride here, I'm going to put the least electronegative atom in the middle, and then I'm going to array my fluorines around in my structure here. Adding up all the valence electrons in this structure gives me a total of 40 that I'm going to have to distribute, and that's going to be cut down right away to 30 because each of these fluorines needs a single bond at least to the central atom here. Then if I go through the work of putting all those lone pairs in, what I'll find is that I actually do end up using all 30 of my electrons in this case, so we're left with 0 there. So once again, we have 5 charge clouds around our central atom, just like we did with 2 of our other examples already, and we're going to end up with a trigonal bipyramidal electronic geometry here. This time, though, all of our charge clouds are bonded groups, and whenever that happens, we know that the molecular shape is going to be the same as our electronic geometry, because we don't have to account for excluding anything on the basis of just being a lone pair. So our molecular shape is also trigonal bipyramidal in this case. And hopefully it also follows from here that because we have a symmetrical shape where there are no lone pairs causing asymmetries in the electronic geometry there, and the fact that we have all of the same atom as our bonded groups around the central atom here, that will give us a conclusion that we should have a nonpolar molecule here. So that's our first example of a nonpolar molecule. And to state that again, the reasons for this is that the geometry is symmetrical and that the bonded groups are all the same. And just as a note here, I'm putting in these notes mainly just to show how easy it is to eyeball these things in certain cases like the ones we've seen so far. If you wanted to add up all the vectors having to do with each of the dipoles in these structures by looking at the individual bonds, you could absolutely do it that way, and that would be the most rigorous approach. But I'm showing you some shortcuts here that will hopefully be helpful in solving these problems rather quickly. My final example here is going to put sulfur in the middle, and then I've got 3 oxygens around it, and I have to count up the number of valence electrons we're dealing with here. That's going to give me 24 if we just count the atoms here, plus an extra 2 because we have a charge of -2 on this ion. So we end up with 26 total. And I'll get rid of 6 right away because I'm adding single bonds once again to my structure. That means we have 20 left over, and if I add those to the outer atoms first, I'll end up putting 18 around the outside, which leaves 2 to go in the middle. And because sulfur doesn't have a complete octet yet, we're probably going to put those on sulfur first. And if we just assess how everything looks right now, it looks like we have completed octets for everything. It's worth noting that this is one example where minimizing formal charges and putting them in the appropriate places here is something that would cause us maybe to write this structure a little bit differently. And just as some review for that, I'll do this now. If we actually assess the formal charges on all of these atoms right now, we should end up with formal charges of -1 around each of the oxygens. And you can do this for yourself as an exercise for the viewer. On sulfur, we should also have a formal charge of +1. And this, just to stress again, is a valid way to draw this structure. all the octets are satisfied, and some chemists might argue that this is actually the more accurate way to display the structure. But if you were told to minimize the formal charges here, we would actually go ahead and take one of these oxygens and convert one of its lone pairs into a double bond, and that would actually revise the formal charges on both of those atoms that are involved there. And what we should end up with is formal charges of 0 on both of them. One final note here is that because this is an ion, we don't expect all the formal charges to be 0. It's just that now the -1 formal charges here are carried by the oxygens, which are the most electronegative atoms in the compound, and everything else in the compound is 0, which is definitely the best we can do here. So to finish the structure, I'm going to get rid of these formal charges and add some brackets so that we're displaying this with the appropriate level of rigor here. And now we just have to determine what the shape is. So to begin with, this is a much more sort of familiar and normal shape to be seeing here. We've got 4 charge clouds around this sulfur atom, and so we should end up with a tetrahedral geometry. And because we have one lone pair, we know that we need to modify what we are saying about the shape. It's going to be a similar shape, but we call this one trigonal pyramidal. Once again, because this is an asymmetrical shape, we can tell right away that this one is going to be polar, because that one lone pair is definitely going to ruin the symmetry of this structure and cause the dipoles not to completely cancel out. All right, so hopefully that's some good practice for simple atoms that have some pretty complex molecular shapes here. And what I want to end with is looking at a structure that is more complicated and has multiple central atoms in it. So for this, we're going to use an organic molecule here, which will actually make our job a lot easier when it comes to assigning the individual geometries and shapes. But I'm going to go ahead and draw the Lewis structure of this compound, and I'm going to use sort of the form that is given in the formula to help me build this in the way that it's intended. So this is a pretty common practice in organic chemistry, giving the structure sort of blocked out in the formula like this. Based on what I've been given here, I know that I need to have a nitrogen bonded to 2 hydrogens, and then I need to have a carbon, which in this case it's explicitly told to me that this is going to be triple bonded to another carbon, which again will be bonded to another carbon after that, and that carbon is going to have this COOH group sort of formed with it in the center. So what that indicates to me is that I'm going to end up with a double bond to the carbon and a single bond to an oxygen, which finally is going to have a hydrogen attached to it. Now that's just sort of some assumptions being made because the COOH group is so common in organic chemistry that I know for sure that that's how the bonding is laid out. Hopefully that's fairly obvious from the blocking in the formula as well, now that we've seen these things a few times. This Lewis structure is missing a couple of things, but because we know the really predictable types of bonding and lone pair arrangements in this structure, because we're dealing with something that's organic and is most of the time going to adopt really predictable patterns, I'm going to go ahead and add a lone pair on my nitrogen, 2 lone pairs on each of my oxygens, and then I can be fairly confident that all of my electrons are accounted for here. I could do the raw math and figure it out, and I'd encourage you guys to do the same thing to check on this. The total number of valence electrons that we would expect to have in this structure, if you added everything up, is 32. And hopefully, if we double check that number, we should see that we have the same amount of electrons accounted for in our Lewis structure. All the formal charges of 0, because I've followed the rules that we talked about in class. And now the job is just to figure out how many of these are central atoms, how many of them we have to pick electronic geometries and molecular shapes for. A central atom here, just to review that concept, is anything that's bonded to more than one atom. So it looks like we have a number of them that we have to consider here. We have this nitrogen that's bonded to 3 different things. We have this carbon that's bonded to 2 different things. Another carbon bonded to 2 groups. A carbon in the middle here, and an oxygen on this side. Everything else has bonds, but only to one other atom. So we don't really consider those as influencing the geometry of the structure, even if they have different numbers of lone pairs on them. So let's go through this in turn and take a look at each of these central atoms and come up with a list to finish off this example. For nitrogen, hopefully what we can see is that we have 4 charge clouds where 3 of them are bonded groups and 1 of them is a lone pair. That should say the molecular shape should be trigonal pyramidal. And for what it's worth, the electronic geometry there is tetrahedral because we have 4 charge clouds. Next, we have a carbon that has 2 bonded groups and no lone pairs around it. And that's the simplest possible thing we could imagine. Both the electronic geometry and the molecular shape are going to be linear in this case. The next carbon looks exactly the same, so it is also going to be linear. Then central atom number 4, with the carbon that's attached to multiple different things here, has a slightly different arrangement. It has 3 charge clouds, and all of them are bonded groups, so both the electronic geometry and the molecular shape here are going to be trigonal planar. Finally, we have an oxygen that once again has 4 charge clouds around it, but 2 of them in this case, and this is the first time we've seen this so far, are lone pairs. So when you have a tetrahedral arrangement of charge clouds, and 2 of those charge clouds are lone pairs, you end up with a shape that is bent. The electronic geometry there is tetrahedral, but we have to remove 2 of them, just to remind everyone, to get that bent shape, ultimately, because we have 2 lone pairs taking up space. So we went through this last example pretty quickly, but I'm trying to illustrate how quickly we can make these decisions once we kind of get a hang of understanding which term goes along with which type of bonding and lone pair geometry that we see. So those were the examples that I prepared for today. I hope these were helpful to take a look at as you're reviewing. And with that, I'll just say thanks for watching, and I'll see you in the next one.